Selena, I don't know if you saw my reply to your email.
No, I didn't.
You did?
I did not.
Did not? Okay, no problem. Yeah.
Okay. Thank you.
Mm-hmm.
So you want to check to see what happens?
Do what?
Because I did like.
Not today. I want to get a chance to do it myself first.
Oh.
But I'll get to it.
Today's the 24th. Are there any questions? All right. We need something that actually picks up the marker dust. All right, so we left off with, we dealt with springs and simple harmonic motion, so let's take a, and we also looked at the person falling through a hole, where clearly we have the position of the object is directly proportional, although in the negative, of the acceleration. So let's take a look at another situation that almost works. The simple pendulum. So what would you guess makes a simple pendulum simple?
It ain't hard.
Okay, that is definitely true. In probably whatever respect you want to use it.
There's only one weight on the end of the pendulum.
All right, so modifying that slightly, all the mass is concentrated at the swinging end in a point mass. So it has no size at all. Point size, there I am again in a point mass. And again, a point mass is just, you don't have to worry about the dimensions of it. We assume that all the mass is concentrated in some indescribably small spot. Not so small that we're creating a black hole or anything like that. All right, so what else would make it simple?
Moves in one direction.
Yeah, it's almost gonna move in two directions, isn't it?
Yeah, typically two directions. I'm trying to think how one direction would work.
Maybe just one mass.
just one mass.
Yeah.
I think that's, all the mass is, considered in as part of this point mass, so I think that covers the one mass idea. So we've got the classic. What's the classic thing that gets ignored in most physics problems at this level?
Air resistance?
Yeah, no air resistance. And throwing in there also, no friction. Now for the bomb that's in the air, it has, that would be the part that has the air, no air resistance, and then friction up here. There's no friction at the fulcrum. So we're dealing with this sort of ideal. There's some planet below. That's really not part of the simple pendulum, that's just something that's gonna have to be there in order for the thing to actually swing. Now, when you're dealing with a simple pendulum, or pendulums, whether it's simple or not, the position is often just indicated by that angle right there against the vertical. There are a lot of things, especially when you do projectile motion, where you typically, not always, but typically give the angle with respect to the horizontal. With pendulums, you typically give the angle with respect to the vertical. So if you pull it back 30 degrees, that's 30 degrees from this central line right here. All right. Let's bring back some memories. What are the forces acting on this mass?
Gravity.
I'm gonna nitpick that, even though this is only our 5th day together, but I'm still gonna nitpick it. What's the force?
Gravitational force.
That'll buy. Gravity is a huge topic, of which the force is one aspect of it. And if I'm close enough to the planet's surface, what do we call that gravitational force typically?
Weight.
Yeah, it's the weight of the object. So I have this weight of the object acting down. It's not in free fall, so it's gotta be something else. What else? What's another force acting on the bob?
Tension.
Acting which way? You can,
Opposite, so we'll be pointing out to the.
okay. Where those two should be at the same angle, so this angle right here should be theta. And tension. Is it in equilibrium? If I pulled it back and let go, would it be in equilibrium?
No.
Why not?
Because it's moving.
No, not the reason why. Unless you want to throw something else on top of that. What does equilibrium mean?
The forces are equal.
Okay,
They cancel each other out.
all right, so can these forces cancel each other out?
Yes.
Those, yes?
Yes.
All right, so when you're adding vectors, how do you head to tail? Does that bring back, are you good with if I talk about adding vectors head to tail?
No, isn't it tip to tail?
Say it again?
Tip to tail. Yeah, vectors tip to tail, correct?
Tip to tail, yeah. All right, so if I add these tip to tail, I draw my tension down, and then I add my weight to it. If this were equilibrium, where would I end up?
Back at the start?
Yeah. There's no way that I can take something at that angle and add something that's vertical to it and end up back where I started. So, some of the forces is non-zero. Let's just put a little side note over here as a reminder. Equilibrium. Total force? is equal to 0 newtons. If the total force is 0, what else also has to be true based on Newton's second law?
Acceleration has to be 0.
Okay. And based upon the definition of acceleration, if acceleration is 0, what else has to be true?
Velocity has to be constant.
Yes. Which I'll write as the change in velocity is 0. If any one of these is true, the other two are automatically true. So it's not a matter of whether it's moving or not, it's a matter of whether the velocity is changing. And the velocity has to be changing because if I let go of it, it starts at rest and then starts to move. So its moving is not as important as the fact that the velocity changed. Or I probably would have accepted it started to move. All right, so it's not an equilibrium. If it were an equilibrium, I'd pull it back to there, I'd let go, and since it's at rest, it would stay at rest, and it would just stay like that. And that's not my experience with pendulums. If you have a different experience, then film it and show it to us. All right, so we have these two forces acting on it. Which way is it going to? Well, I think we know which way it's going to move. There are two types of acceleration involved here. What are the two types of acceleration involved? Or tell me one of them.
Gravity, gravitational acceleration.
Rotational acceleration?
Is that gravitational acceleration?
Oh, gravitational acceleration? No, even though acceleration due to gravity or gravitational acceleration, the little g is going to show up in the equation, that's not really the acceleration it's experiencing unless it's in free fall. Or the only force acting on it is its weight.
In the X and Y direction?
Which are the x and y directions?
Whatever you make them, I guess.
What do you want to make them?
X is left to right, Y up and down.
Is there a particular reason why?
Math. I've been brainwashed.
At least you recognize it. It's the first step to recovery. So there's acceleration, horizontal and vertical acceleration.
Do what?
There's horizontal acceleration and vertical acceleration.
Yes.
I will tell you, yes, technically that is true, and this is probably a very difficult way of approaching the problem. What might be a better way of doing the coordinate axes so that the math might be simpler?
Just make it horizontal.
Rotate the point.
Yeah. You said negative horizontal?
No, I said ignore vertical.
Oh, ignore the,
Ignore the vertical.
well, we can't just exactly ignore vertical because go in with the hand gesture in the back. Setting that up as the coordinate system probably is going to make more sense. So we have pointing towards the pivot point and then perpendicular to it. The advantage of using I hat, J hat instead of X and Y, hopefully break yourself of the brainwashing without being kidnapped in the middle of the night and deprogrammed. I don't know, is that still a thing? I'm guessing not.
What?
People joining cults and then the parents want them back, so the parents come in, they hire people to kidnap them and then deprogram them from their cult beliefs. It was a 70s thing.
It's all right, I know what you're talking about.
All right. All right, so if we break it up into those coordinate system right there, we will actually have acceleration in those two directions. Now, a coordinate system like this is it's a changing coordinate system, but all we care about at the moment is just this situation. So if I have this acceleration pointing towards the center, what is that acceleration called? This is a flashback to 131. Apparently too long ago. All right, let's hopefully ring some bells here. What's the definition of acceleration?
Change in velocity in a direction.
The first hour for the definition.
Well, what did you say?
You said change in velocity and direction.
Change in a velocity in a direction.
Okay. Acceleration is related to change in velocity, but that's not the definition of it. You left a piece off.
Over time.
Yeah. All right, so change in velocity over change in time. Velocity, so this is velocity, and you know it's velocity because I got a vector symbol over it, and I'm using a V. Velocity. What is velocity?
How fast something's moving.
All right, so speed
In a direction.
in a direction. The direction is critical here. So when I have a change in velocity, if I have a change in speed or a change in direction. So if the speedometer in your car changes, you have an acceleration. If you're going around the corner, you have acceleration. Now the acceleration related to change in direction, that would be the acceleration in the j-hat direction. So the question is, what is that acceleration called? While you're thinking about it, I'm gonna step into the other room and grab my book so I can figure out what chapter it would have been. That would have been Charlie, chapter 10. Yep. Chapter 10. You can italicize it in summary. I was hoping one of these things would just jog a memory here, but at this point, someone's about to tell me. And that when that person tells me, that person is going to pronounce it correctly. Or clearly so that I can understand what word they're using.
Is it centrifugal force?
That's, acceleration.
Centrifugal acceleration?
So if I have a change in velocity because of change in direction, that creates a centripetal acceleration. It is caused by a centripetal force.
I actually didn't look that up in the book, I just remember that.
All right, good. If there's a change in the speed of it, what kind of acceleration is that?
Positive.
Pardon?
Positive.
Not necessarily. Maybe right half the time. Or actually, it depends on how you define your positive and negative directions. when you first dealt with acceleration, what kind of acceleration were you working with? I suspect it was like chapter 2 or 3.
Horizontal acceleration?
Not,
Like normal acceleration, I suppose, I don't know what you.
normal as in perpendicular or normal
Yeah.
as in regular?
What's the difference?
Well, I mean, normal, there are multiple definitions of normal. One definition of normal means perpendicular. Another definition of normal means usual or typical.
Typical.
Okay. So regular old acceleration, there actually is, there's it down, it's called tangential acceleration, but typically in the early chapters, it's just called acceleration. But since we have another type here, let's differentiate, this is tangential. Tangential acceleration. Because it's tangent to the path, because this mass here is going to move in an arc. And the change in speed deals with the acceleration in that direction, whereas the centripetal acceleration deals with the change in that's perpendicular to the movement. What I care about here is just the tangential acceleration. So when I break it up, when I have these vectors here, I'm going to break them up into components. I need to figure out how much is in the direction of movement and how much is perpendicular to it. And I'm going to redraw that into bigger. All right. Because we have issues here. All right, sometime within the next minute, if a warning sign pops up, if you let me know, please. And I think I forgot to dismiss. Yep, I dismissed. All right. Because the last couple times that it had an error, it was right after it finished the first